With the help of electronic configurations that we have learned, we can understand some of the properties of elements on the periodic table. What we are going to learn, the properties that we will learn about in this class: atomic radius, metallic character, ionization energy, and electron affinity. So the first one that we'll talk about is the atomic radius. This is, just like it sounds, radius of the atom. Distance from the center of the atom to the outermost electron or the valence electron. Now, how do we know how atomic radius changes along the group, down the group, and along the period? First of all, period is the horizontal arrangement and group is the vertical arrangement. Okay, so there are many groups and many periods in the periodic table. We discussed that in class. So then think about it. Say, let's talk about group 1: hydrogen, lithium, sodium, potassium. They're all in first group, group 1. So what is the configuration of hydrogen? 1s1. What is the configuration of lithium? We have done this before. 1s2, 2s1. What is the configuration of sodium? 1s2, 2s2, 2p6, 3s1. What is for potassium? 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So if you think about it, if you check the pattern that is going on here, the first thing that you observe is the last electron or the valence electron is not paired. The valence electron is in the s subshell. The main shell for the valence electron is increasing as you go down the group. So this is 1, 2, 3, 4. Pictorially try to represent this: hydrogen, 1 shell, lithium, 2 shells, and this is where the valence electron is. This is again symbolic representation. The orbitals are all three-dimensional in nature. We're trying to symbolically represent this. Sodium, 3 shells, and the valence electron is in the 3rd shell. So the distance between the central atom and the valence electron is increasing as you down the group. That means atomic radius increases down the group. Okay. Now, by the same account, if you look at, say, let's take the example of 3D series, right? Scandium, titanium, vanadium, chromium, all the way up to zinc. Okay, so scandium 21, zinc 30, titanium 22, zinc all the way to 30. So scandium valence configuration 4s2 3d1, titanium 4s2 3d2, vanadium 4s2 3d3. So if you notice again, the last electron that is coming into the atom is entering 3d. Okay, so it is pretty close. It is, if you think in terms of distance And pictorially, if you want to visualize it, this is the nucleus, first shell, second shell, third shell, fourth shell, and 3D is somewhere here, right? So the last electron is coming into roughly the same distance, roughly, not all of them at the exact same distance, but roughly the same distance. So what is happening is that the last electron is coming pretty much, so there are 10 electrons that are being filled at the same distance, and there are a lot of protons here. Protons are increasing too as electrons are increasing. So because the protons are increasing, attraction towards these electrons is more. See, if the electrons were going into farther and farther shells, attraction would not be more. But these are not going farther and farther. All of the 10 electrons are coming into the same subshell, the same orbital. So what's happening, or the same subshell, I would say same subshell. So what's happening is that the attraction is higher. So these protons, or this nucleus, will actually attract these electrons towards itself. So the distance gets shortened up. Okay. So with all this visualization, what you have to remember is that there is no line like this in real life. There is no line here. Wherever the electron is, that will be considered as this distance. So there is no real boundary. There is no physical line here. Wherever, if the electron is here, this becomes the orbital. If the electron is here, this becomes the orbital. And the presence of electron is again dictated by the total number of electrons, the total number of proteins, the energy of the electron. So the distance would be determined by all this. So coming back to our question in discussion, because the 10 electrons are coming into the 3D subshell, the attraction of nucleus towards these electrons is high. So the nucleus is attracting these electrons towards itself. So the distance between the valence electrons and the nucleus is shortening. So, but it's not a remarkable decrease, but it is a considerable amount of decrease. So as you go from left to right on the periodic table, as you move along the period, the atomic radius decreases. The trend for atomic radius decreases along the period, increases down the group.